In our project, we modeled and optimized a district heating network. In a district heating network, waste heat from a plant is used to heat different households in a certain district. And first we made a model. In our model, we used one heat source, 10 consumers, a heat reservoir, where energy can be stored when the demand is lower than the supply, and pipes that connects the different components, of course. Afterwards, we did a static optimization to optimize the dimensions of the pipes, the heat reservoir, and the heat exchangers. We did this by minimizing, on the one hand, the heat losses, and by maximizing, on the other hand, the heat exchange between the consumers in the network and the heat source in the network. And afterwards, we did a dynamic optimization, where we try to control all the mass flows in the network, and we designed a modal predictive controller for this.
The first two components that we'll discuss are the heat source and the consumers, because they are actually pretty similar. They can basically be modeled as simple heat exchangers. We have implemented them by using the NTU method for heat exchangers of the counterflow type. We don't have enough time to go into the details of this method, but it's exactly the same as we have seen in some other courses. As can be seen on the figure, a heat exchanger exchanges heat from a hot side to a cold side, and we want to know the amount of heat that is transferred in these components. In the heat source, the source is of course the hot side of the exchanger, and we want to determine the amount of heat that the source adds to our network. Therefore, two input signals are needed, namely the temperature at the inlet of the hot side and the mass flow rate at the hot side. And the mass flow rate and inlet temperature at the cold side follow directly from the demand of the consumers and the system dynamics. In a consumer, things are turned around, thus the consumer is then the cold side of the heat exchanger. Again, two inputs are needed, the mass flow rate and the inlet temperature at the cold side, and the mass flow rate and the inlet temperature at the hot side again follow from the system dynamics. So when all of these signals are known, all of the inputs that are needed for the NTU method are determined. So we briefly discuss how these signals are determined. For the heat source, we could simply search for data of industrial waste heat sources on the internet for both inputs. That was very hard to find. We did find some data on waste heat itself. By interpolation of this data, a heat function could be determined. We then simply said that the temperature at which the heat was available was 500 degrees Celsius, which is a typical value for industrial processes. And based on the heat and the temperature, a function for the mass flow rate could then be determined by applying some basic formulas from thermodynamics. For the consumer, we again chose a typical value of the inlet temperature, this time at the cold side. In the consumer, we started from a certain set temperature and an outside temperature. Based on the difference of the actual temperature inside of the consumer and the set temperature, and some heat loss due to temperature difference with the environment, we could determine the heat needed to heat up the consumer. When combining these results with the inlet temperature, the mass flow rate at the cold side could be determined, and from the heat needed to heat up the house or the consumer, the mass flow rate that the consumer should tap off from the network can also be determined. So M subscript H. And the mass flow rate at the cold side in the heat source is then the sum of all the demanded mass flow rates by the consumers.
The heat reservoir in the model is used to store energy. In the case that the demand is lower than the supply, then the heat reservoir or tank will charge, and in that case, hot water will flow into the tank and cold water will flow out of it. In the other case, when the demand is higher than the supply, then the tank will discharge and cold water will flow into it and hot water out of it.
The simulation boils down to putting all the components together and connecting them in the right way, and then let Simulink do the rest. Here we see two plots of the temperature in two different consumers for one complete day. The yellow lines are the functions for the set temperature. The blue lines indicate the actual temperature throughout the day for the consumers. Of course, we want the blue line to be as close as possible to the yellow line. As can be seen, the actual temperature follows a setting to a certain extent, but there is a big offset and some sudden changes due to influences of changes in the other consumers. Clearly, there is a lot of room left for optimization.
We divided the optimization into a static and a dynamic part. In the static optimization, we'll assume constant input signals and we'll determine the optimal values for some important parameters in the model. Looking at the heat reservoir, it is both important to minimize the losses, which are proportional to the surface area, and to maximize the volume, to store as much heat as possible. There was no absolute minimum for the relationship between the volume, the surface area, and the diameter, so we scaled volumes used in practice to our case, and that is how we obtained the optimal value for the diameter of the cylindrical heat tank. In the pipes, we wanted to find the optimal diameter to minimize the heat losses. These heat losses depend on the length, the diameter, and the time delay. However, when the term for the time delay was expanded, the diameter cancelled out, which is why we chose a diameter that resulted in the smallest cost. In the heat exchanger, we want to maximize the heat transferred, all while minimizing the cost. Both these factors depend on the surface area, and the cost could be assigned to the transferred heat, so we found the optimal exchange surface area by determining the break-even point. As I mentioned before, the heat losses in the pipes are also proportional to their length. Another thing that causes losses are valves. So we tried to find the optimal network by looking for the right balance between the length of the pipes and the number of valves. We simulated two different setups, one where the piping elements are shorter but using more valves, and one with less valves and longer pipes. Sadly, while doing this, the simulation time considerably increased, which is why we chose to continue the dynamic optimization with only 5 consumers.
For the dynamic optimization, a MIMO controller is added to control all mass flows to each consumer. Now, in case of sufficient heat supply for all consumers, this is a trivial control problem. However, in case of insufficient heat supply, not all target mass flows can be reached. Ideally, closer consumers would be prioritized to minimize total heat losses in the pipes. Now, this can be done by using an MPC controller with a custom cost function in Simulink. This cost function penalizes high mass flows to further customers. Unfortunately, Simulink plots to demonstrate that customer prioritization wasn't possible due to exceedingly high computation times. With this, our presentation of district heating networks is concluded. Thank you very much for your attention.